With this video, we're starting the topic of equilibrium, which actually covers several chapters in your textbook. Equilibrium, solubility, acid-base, buffers, all of those things relate to equilibrium. And you can more or less guarantee there's going to be equilibrium in the free response where you're doing some calculations, maybe some explanations as well, in addition to lots of multiple choice because Big Idea 6 and the AP curricula is split into 6 parts. 1/6 of it has to do with just equilibrium, so a major idea. So to make sure we understand what that means, so the question, what is equilibrium? You can read a dynamic state and balance in which two opposing processes occur at the same rate. So I've got all arrows going all over the place here, and I've got 3 different examples here. In each case, it's kind of one thing pushing one direction, something else coming back the other direction. So when you're running on a treadmill, you're staying in the same place because the treadmill itself is going at a certain speed in one direction and you're traveling, hopefully, at exactly that same speed in the other direction. You're in this state of balance. You've got those opposite things going at the same speed. A damp towel and a closed gym bag. There's actually a really good animation that I will probably show in class or link that explains equilibrium in a minute or a minute and 30 seconds. But the idea is kind of what you see over here, that if we have these water molecules here, some of them will evaporate, but then when they evaporate, others will condense. So, okay, these evaporated, they're condensing. Well, now this guy who's saying I'm getting out of here is going to evaporate. You've got evaporation and condensation kind of opposing one another happening at the same time. If cars are crossing a bridge, if you have the same number going one way as the other, you could think of that as a type of equilibria. And down here I've got this picture. I was kind of trying to fit all these things onto one page. If you're putting as water into that container as quickly as it's going out, the opposing processes of filling and emptying are occurring at the same rate. So the idea with chemical equilibrium is we know certain things about what the opposing processes are, etc. So the opposing processes are the forward and reverse reactions. So any chemical bond that we break could also, with the right conditions, be made. Every bond that could be made can be broken. Almost every reaction in the right circumstances is reversible. So most of the time we'll write them instead of with just a left or right arrow with this reversible arrow. So this is kind of where we take stuff from Chem 1 and we say, okay, yeah, that was a simplification of what it really is. So these reactions really are going to be reversible. Reactants turning into products, products back into reactants. That's what it means to be opposing processes here. Dynamic means that it's still happening. You could stand on a treadmill with it being off and nothing happen there, but it's not dynamic. You're not moving, the treadmill's not moving. In terms of a chemical reaction, that means the forward reaction's happening and the reverse reaction's happening. We don't just mix 2 chemicals and then they're done. The process just keeps going. And because it's at the same rate, the forward and the reverse are happening not just at the same time, but at the same speed. We are making products as quickly as we are consuming those products. We are turning products back into reactants as quickly as the reactants are turning into products. That leads to a certain amount of balance. Right here, the same amount of water in as water out, that water level is going to stay the same. So if we get a little bit more specific here and talk about chemical equilibria, we see the definition. The forward and the reverse reaction rates are equal. The concentrations remain constant as a result as long as we're at constant temperature. So we've got some important things here that we will mention over and over and over again, and probably not really that many overs, but we'll mention several times. The rate is equal. The concentrations are constant. So it's not that our concentrations are equal, it is over time the concentrations stay the same. So for all the math we've done up till now, and really all of Chem 1 math, so when we're doing stoichiometry, we think about things that go to completion. All the reactants go away to make products. Sometimes we have a limiting reactant there, but we're just going one direction. These don't go to completion because we don't use all of our reactants and because our reactants turn back into products. So we don't make as much product as the limiting reactant would lead us to believe. So to get to equilibrium, we have to have certain things happen. We have to understand what it would look like. We have to understand what is happening. So when you're at equilibrium, the way you're going to recognize that it's at equilibrium is that it's going to look the same. So when we do a normal chemical reaction, we turn reactants into products and then it's done because we have our products. That either could be a one-way reaction or it could be an equilibrium. We don't see anything else changing. We don't see anything being made that wasn't there before. So our reactants aren't disappearing and our products aren't forming. As a result, we don't have any more or less gas. We aren't releasing or absorbing any more heat. We're not consuming or making any more hydrogen ion, and our color isn't changing because we're not changing what particles we have or their concentrations of them. It gets to equilibrium when it looks the same. So the process goes, when it stops changing how it looks, we're at equilibrium. When it says here the system has to be closed, that means that there's not chemicals flowing in and chemicals flowing out. We aren't always introducing new things to make the process keep going. So this picture right here would really best be in equilibrium if this was connected back up around here like this. And obviously you're not going to be asked about filling a container and draining that container, but the idea here is that we don't have a new chemical coming in, so we're not making new products and then those products are disappearing. The products themselves are turning back into the reactants. So it's not just a steady state of making this and consuming that, where things are happening constant over time. We are actually you could almost think of it as a recycling process in the back and forth, or maybe even more than recycling, the reuse part of reduce, reuse, recycle. And then the last thing, if it's really at equilibrium, if we do something to it, there will be a shift. So what that means is if I maybe take away some of my products, the reaction will make more products. If I put in more reactants, then I'll be able to make more products. If I change the temperature, the reaction will do something. A one-way reaction doesn't necessarily do that. If I take something away of a one-way reaction, when it's done, it's already done, so it doesn't change. At equilibrium, it's still in that dynamic process of forward and reverse and forward and reverse and forward and reverse. So if I put something in or take something out, it's going to throw off how that looks. So we could think of this as, poking something to see, okay, is that possum or I'm not going to use a possum as an example. Is that animal that's just lying there? Is that snake? Is that dead or is that just asleep? So you poke it, you hope that it's dead, I guess, or maybe you hope that it's asleep, depending on your thoughts on snakes. But you find out, okay, is this thing done or is it still moving, but I just can't tell that it's doing that. That's what this means. Conditions are changed, we see something happen. So for our equilibrium, we're going to use some very simple reactions. A lot of times we're going to be talking about A, B, C, and D, but it could be any reactants, any products that meet those requirements, that can do these things, that are reversible, etc. So the simplest reaction we could think of here maybe would be A and B making AB. So even I think simpler of thinking of A and B making C, because C seems like something new and maybe abstract. AB is obviously the combination of this. So we've got our synthesis, but then it can decompose back into its parts. So if I started this reaction, I would have a container that only had, presumably, my reactants. So what happens is that A and that B makes AB. So as they react, A and B go down, and you can see a slight decrease in font size, and AB starts to appear. That's what we would expect in a one-way reaction, but because this is reversible, I've got this tiny little arrow there. Oh, sorry, thought I was trying to zoom. Tiny little backwards arrow, there we go. Because this isn't just a one-way process. Now that I have a little bit of AB, that AB can decompose. So then A and B keep turning into AB, but as I get more AB, it starts going backwards and making more A and B. When I have only A and B, the only thing they can do is decompose. If I have only AB, the only thing the only thing these do is combine. The only thing this can do is decompose. So as these go down, they combine more slowly. As this goes up, it decomposes more quickly. And at a certain point, the rate at which AB turns into A and B equals the same rate at which AB turns into A and B, and we get to equilibrium. We are still doing the process, A and B into AB, AB into A and B, but the amounts of each are not changing over time. If I thought of this the other way, if I had my reaction, so kind of cross that out for just a second, but if I put AB in my container, then what would happen would be AB would break down, and then it'd get a little bit smaller, and it would make A plus B. And as soon as I had the A and B separate in my container, it would start turning back into AB. So this can work either way because it is truly reversible. So we're going to start to look at this graphically and understanding these that you see right here. These graphs is very important to understand what this really means. It connects us to kinetics in several different ways because we're looking at rates, we're looking at concentrations, we're looking at how they're changing over time. So these are a few things that should be kind of given based upon what we already learned about kinetics. Rate is fast when concentration's high because you have a lot of particles colliding, a lot of reaction happening. If you have fewer particles or as they go away, it slows down. And that's what our graph is showing here. This is the forward is A and B turning into AB. So at the beginning I have lots of A and B that are separate to turn into AB, so I have a really fast forward rate. I have no AB yet. So AB isn't turning back into A and B, so my reverse reaction isn't just slow, it has a zero rate. But as these start to go away, I don't have as many of those particles, so it slows down. As I start to make AB, now that AB can decompose, so it starts being made. This one speeds up, this one slows down. Eventually, by definition of what equilibrium is, we get to an equal rate. And that's what it says. Where is my pen? That's what it says. Right here. Equilibrium is reached when the rate of the forward and the reverse are equal. So rate equal. And you're saying, well, how do I know that? That's what equilibrium means. There's not like in this equilibrium it's this thing and in this one it's this thing. That's the definition of chemical equilibrium. Concentrations are not necessarily equal. That's what we're going to see right here. So we've got two graphs here that are concentration versus time. So when you are given a graph, whether it's an equilibrium, kinetics, whatever it is, very important to read your y-axis. And you know that from kinetics because it depends whether it's concentration, natural log, reciprocal. Which one's on the y-axis gives you the straight line. So just always be in the habit of looking very carefully at your axes. But either of these could be the graph for concentration versus time. What you see is the reactant starts off high and it decreases. So you can see, and even if we were looking at not just that, if we were looking at the slope, we see it starts off steep, and then it becomes more shallow. Obviously, I'm not great at drawing my tangents here, but as time goes, it gets more shallow and more shallow. So look at the slope, it's slowing down. Well, product started at zero, and increased, and increased. We could be in a situation where maybe we had some reactant and some product all in our container at the beginning. We could be in a situation where technically we're starting with the things that are on the right side of the arrow, but really the point of this, or what we're thinking about with this, is the idea that we start with something and something's going away. The other thing is being made. So products are being made, and those level off. I'm using this up, using this up, using this up, and if this were a one-way reaction, we'd use it up, use it up, use it up, use it up, and have none of it. But it's not one way. We use it up, and we still have some left at the end. So that gets used up, it levels off, this gets made, and it leveled off. Equilibrium is reached when this and this and this and this, or this and this, level off, because yes, my reactants are going away, going away, going away, but now the amount that I have is staying constant. Making more and more and more products, the amount that I have is staying constant. The same thing would happen in a one-way reaction. We talked about the other qualifications. If it's dynamic, if it's still going, if we can stress it and cause a shift, then it's in equilibrium. And you can sometimes even prove that mathematically. If you're going, and you still have tons of limiting reactant left over, or you haven't made the maximum amount of product, then that means you're at equilibrium. It's not a one-way. But to highlight the important thing here, equilibrium's reached when the things that are here, concentration of everything is constant. Notice these graphs did not meet. This graph met because rates are equal. These graphs did not meet because amounts are not equal. Amounts are constant. And the reason these two graphs look different is a concept called the equilibrium position. So that's what we're going to wrap up kind of our conceptual understanding, or our conceptual introduction with, is we've got the definition, forward and reverse. Rates are equal, amounts are constant. This turns into that at the same rate that it turns back into it. It's really hard to visualize or see it because we can't see this happening. We can't tell that the reverse reaction's still happening because it just looks like it's done. We'll do some labs where we'll prove this, but even as we prove it, it's not the most obvious thing that you're seeing or knowing, but it's the idea that we're meeting all of these qualifications. But kind of back to what it here on the paper, got a little sidetracked there. The equilibrium position means how much stuff do we have when we are at equilibrium. We know we didn't use all of our reactants. We know we didn't make as much products as possible. But how much reactant did turn into product? So how much product is there? In this graph, we use some of it, and then we have this much, but we only make a little bit of product. Here we use a lot of reactants, so we make a lot of products. The equilibrium position, or that concept, answers this question. Which thing, reactants or products, is there more of when we get to equilibrium? And the answer could be either one. We could have lots of reactants still with very few products, maybe lots of A and B separate with very little AB, or we could have lots of AB, lots of the product with very little A and B. And it depends on the exact reaction. There's not an answer that is right. I can't say, well, you always have this many products and this many reactants, or this always happens in this way. It depends on the exact chemical reaction. It also varies as you change the temperature. Heating it up affects how much energy is there for the collisions, affects how easy it is to break bonds. Cooling it down slows everything down. Fewer collisions, less energy, fewer collisions that are productive. You can determine this quantitatively. We can calculate, I have this much product, I have this much reactant. These are maybe actual numbers, and you make a ratio of what's your ratio of products to reactants. That is called calculating the equilibrium constant. A lot of times it's just discussed qualitatively. Which one do I have more of? Do I have more products or more reactants? And with a general reaction here is reactants making products. If I have a lot of products, like this one would say, I would say the equilibrium lies to the right. I have more products, and the products are on the right side of my chemical reaction. In this instance up here, I still have lots of reactants left with very few products. So we have our three scenarios here. They could be about equal, or I could have lots of R, only a little bit of that, a little bit of R, with a lot of products, and it would just be different ways that different reactions occur. It's definitely important that you understand both of these graphs and the one at the top in terms of where is equilibrium reached, which thing is favored, how much is it favored by, at what time did that happen, which thing was in the container initially. Lots of really good questions that can be asked about these three graphs. And with these three graphs, when I say there we go, we kind of got all three of them there. This graph will pretty much always be the same. One rate decrease, the other increase. And this graph matches with this, and it matches with that. If we had exact values and we looked at the exact amount this was changing versus that, we could get a better idea of which graph it maybe represents it better. But in either case, the rate at which reactants turns into products decreases here as my reactants go down. It decreases here as this goes down. The rate at which products are made increases, the rate at which reactants are made again increases as I have more products. So you will either look like this or this. You can't have both of these for the same reaction, but this is the same for either of them, and that's important. And then the reason this happens, the reason that it's not, well, I have an equal amount of reactants and products, and it's one of these for every one of those, or that it's not always exactly the same. So you got a lot of different things going along with that breaking and making, that thermodynamic, that energy associated with the chemical reaction. It depends on the reactants, their potential energy. It depends on entropy, because if one side has more entropy than the other, that side's going to be favored, but depending on the temperature. Changing temperature changes K, because we are changing our, and not just our entropy, but our free energy. And then it depends on the concentration. High concentrations means faster rate. So there's a lot of different things going on here. So to really quick summarize our intro here, equilibrium is a reversible reaction in which after it's gone on for a little while, both forward and reverse are happening. They're happening at the same rate, not just reaction. They're happening at the same rate, and the amount of each thing stays constant because of that. Because for every one of these I make, I break one back down. So we will get into all of the math of these things, but it's important that you really have a strong grasp on those concepts so that the math and the calculations really mean something.